diagnostic and their practice tests are, but I would imagine this covers the more of the math basics that you need to know.
Okay.
I've been looking at it a little bit, and it looks fairly fundamental. Okay, we look at the first one. A is greater than 0. Which quantity is bigger?
Let's see. That would be quantity A.
Correct, because that's a to the ninth. That's what?
To the 6th.
Okay. And number 2. You see this okay, or do I need to blow it up a little?
No, actually, I can see it fine.
Okay, good.
That one, let's see, A plus B minus C and 0.
I'm sorry, what'd you say?
I'm sorry, I was talking out loud reading the
Okay.
problem.
Okay, I thought maybe I misheard you were giving
No.
your answer and I didn't hear it right.
That one, I think I would need more information.
Okay, this is actually a principle in geometry. This is called an exterior angle, and it's always equal to the sum of those two.
Okay.
And the reason is that C is supplementary to this one. Supplementary meaning that adds to 180. And these two plus this add to 180. So this one plus this one has to equal C. Okay. In other words, A plus B minus C is equal to 0 because C is equal to A plus B. In other words, no matter how I draw a triangle, this angle C is equal to A plus B.
Got it.
Okay.
Okay, so they're equal.
Yes. Now this one wouldn't be very tricky if they said A and B were greater than 1. Because then it'd be simple enough to just pick some numbers, you know, like 9 plus 16. Well, right. we know 9 plus 16 would be 5, the square root of that, and yet this would be 3 plus 4, so this would be bigger. But the fact that they've made these numbers between 0 and 1 means it's a little harder to do that. It's a little harder to come up with numbers that are going to add together and give us a perfect square root, and then each of them also. So it's going to be tough to use numbers here to solve this. The way they suggest solving it is, since A and B are both positive, we can square this side and square this side and compare those two numbers. In other words, and that's legitimate, because if I say 3 is greater than 2, then when I square this, it's always going to be bigger than when I square that. Well, if we square both sides, what do we get on the left?
A plus B.
What do we get on the right?
Also A plus B.
Actually not. Let's go through this, because this is an important principle to learn.
Okay.
When you square a binomial, that is not equal to x squared plus y squared. In other words, if you FOIL that, you will get x squared plus 2xy plus y squared.
Correct.
That's worth memorizing, as well as this, because you don't want to have to FOIL this every time. And this is another one of those things where it's presented to you so frequently, and sometimes in backwards mode, that it's worth knowing this. In other words, sometimes they'll give it to you. Now, hold on. Let me shut my camera off again. You don't need to see me. My computer's acting up. So, knowing that whenever we have a binomial that we're squaring immediately goes to this is very valuable. More valuable than always having to go through the FOILing process.
Okay.
And I'll give you a perfect example. What is 100 squared minus 2 times 100 times 99 plus 99 squared equal to? Now, this might look like, well, I can do that on a calculator pretty easily. Maybe. This problem actually came from a GMAT test back when GMAT didn't allow calculator use. And in fact, I'm kind of thinking that this must be new on the GRE too, because I tutored a GRE student a few years ago and she was not allowed to use a calculator. I got a feeling they've changed it recently.
Yeah, in fact, they just updated it, I think, in 2012.
Okay, that makes
or 2011.
That makes a lot more sense to me, because it's such a completely different test when you can use a calculator as when you can't. And so they have to gear all the questions to be different. So this was an excellent question on a test where you couldn't use a calculator. How good it is on a calculator test, I don't know, because you could just plug this in and figure it out, although it's not that easy on a calculator. You got some pretty big numbers you're dealing with. But the way that they originally wanted you to solve this was recognizing that it was that. This 100 squared minus that is exactly that, which means this has to be 100 minus 99 squared, or 1. So without using a calculator, I know this quantity has to be 100 minus 99 squared, because it's equal to x minus y squared. And I can do this math in my head. So it's questions like this that make it valuable to know these two by heart.
Okay.
So that when you see it in this mode over here, you'll recognize it. Whereas if you only had experience FOILing, you wouldn't be able to do that. Okay, so back to our problem. Let me go down page here. If the left side of the equation is a plus b, and the right side of the equation is a plus 2 square root of a times square root of b plus b. Notice that when I square that using my formula, I get this.
Okay.
Okay? So if, I shouldn't have put an equal sign in there. I'm trying to compare these two quantities. There's the left quantity, quantity A, and here's the right quantity after we've squared each. Well, we know A and B are positive, so these two must cancel out, and what we have left on the right is 2 times a positive number times a positive number. As long as A and B are positive, this amount right here is going to make the right side greater than the left side.
Got it.
Okay, number 4. There are a bunch of people in line. How many people or how many numbers are between these two numbers?
Actually, it's going to be 101, isn't it?
It's 100 minus 1.
100 minus 1.
In other words, that's difficult to figure out because we don't want to have to count them all up.
No.
So let's see if we can come up with a smaller, this is always what you want to do. How many numbers are between 4 and 2, or 2 and 4?
Including 4?
No. In other words, in this problem, they want the number of people between Jack and Jill. So
Okay.
they're not counting Jack or Jill. So it's the same question as the number of numbers between 25 and 125, not counting either number.
Okay, so there'd be 1.
Okay, and we got that by subtracting the two numbers and subtracting 1.
Okay.
In other words, if I said how many numbers are between 2 and 5, you'd say 5 minus 2 minus 1.
Okay.
Okay, so if we apply that principle that we can easily gather from very small numbers to these two big numbers, then we know there must be 99 people in between them.
Okay.
Okay. Do you work with spreadsheets at all?
No.
Well, a very common spreadsheets are merely rows. And you might have a spreadsheet that has 2,000 rows in it. And so you'll have row number 2, and way down here you'll have row number 463. Well, I work a lot with spreadsheets, and it's frequently very valuable to know how many rows are in between there.
Right.
So I am used to doing this, where you subtract the two numbers and subtract 1
That's a good
from
principle
that.
to know.
It's a good principle to know, yeah. All right, let's look at this one here. Now, these are actually, I like these diagnostic questions a lot. They force you to cover some of the fundamental math that is in a lot of the questions.
That's making me realize I don't know a lot.
Well, I figured this was really where we should have started last time. I just hadn't had enough time to review this book to see where a good starting spot would be. But
Well, and I definitely knew I needed help. This is proving it.
well, these are not that easy. These are somewhat difficult.
But that's what I want, because I would really like to ace this test when I take it. So
Okay. When are you taking it? Do you have it scheduled?
right now I've got it scheduled for June 29th.
Okay.
Thankfully, I can actually push it out. I don't have to have it done then if I'm not ready. But I'd like to be able to take it then.
Uh-huh. On this problem here, since x is greater than 90 but less than 180, then we have a variety of ways that we can draw this picture. We could draw it like this. Okay. So they want to know whether the perimeter of this triangle is greater than or less than 17, basically.
Okay.
Oh, man, hold on. I'm going to have to move my mouse out of the way. Sometimes my mouse interferes with my cursor, and I have to move it across the room. I think it has to do with the frequencies they transmit their signal at or something. Sometimes my computer just goes haywire when I have them anywhere in the same vicinity. I hope it doesn't give me any trouble here. It might, probably the easiest place to begin with this problem is to assume that x is 90 degrees. And
Okay.
that's a difficult assumption to make because right off the get-go they tell you it's not. It's greater than 90 degrees.
Right.
But if we could take the 90-degree angle and find out something about its perimeter, we can tell that any triangle that we create where x is greater than 90 has a bigger perimeter than this one. You see why? In other words, the perimeter of this triangle here, all radii are equal. So this is still both 5.
Okay, got it.
Like this one. Clearly, as the angle of x increases above 90, this third side gets longer. Okay? So let's figure out what the perimeter of this is. So if we have a triangle, and we know this must be a 45-45 right triangle. If I look at just this triangle here, now you realize why that's 45-45?
Yes.
Okay, because it's isosceles, and not only does the radii equal the radii, but those opposite angles are equal to one another. Okay, if we want to figure out the hypotenuse of that, what is it?
It's going to be 5 the square root of 2.
Okay. And did you get that from applying the Pythagorean theorem, or did you get that from applying similar triangles?
Similar triangles.
Okay. I like that similar triangles method better myself. It's a little easier, but we could just as easily have gotten 5 root 2 with the Pythagorean theorem. So the question is, what is 5 root 2? You have your calculator, or you probably should have a calculator in front of you that's going to be the equivalent of the one you're going to use on the test. I don't know if you can even do that. Probably not, because you said it was built into the computer, huh?
Right. It's right into the computer. Yeah, it's really, really, really a basic calculator, too.
Okay. Well, if you have any calculator available at all,
I do.
Let's go ahead and use it. We won't use any of its sophisticated techniques, but it surely lets you do 5 times root 2.
It does, and that would equal 1.14869.
Times 5.
Right.
Which is?
Well, actually, let's see, 5. Yeah, see, no, that's actually already multiplying it by 5.
Well, the square root of 2 is 1.4 and change.
Oh, I keep getting an error syntax.
Here, let me do it on mine. Although this is good, we need to
Practice with it.
Yeah, exactly. We want to make sure you don't run into any problems. So when I take the square root of 2 and multiply it by 5, I get 7.07 and additional decimals. But that's all I really need, because it's asking us to compare the perimeter. Well, even when I make x 90 degrees, the perimeter is 17.07, which is greater than 17. And as x gets bigger than 90, this third side merely gets bigger, so it always has to be bigger, the perimeter of the triangle. In other words, as long as 5 root 2 was a number greater than 7, even if it was only greater by 1/billionth, then that would have been enough. Okay. This illustrates kind of another thing that used to come up in a lot of GMAT tests. That sometimes when they give you a parameter like this where it says x is greater than 90, you have to consider looking at, well, it's more easily analyzed when x is equal to 90. In other words, if I make x equal to 90, I can easily figure out the dimensions of side AB. Whereas it's hard to figure out the possible dimensions of a side AB if I restrict x to only greater than 90 and less than 180. All right, let's see.
So in this case, would I try to solve?
Yeah, in other words, it's going to be real hard coming up with an arithmetic mean of B and C when we're looking at it in this format.
Okay.
Okay, so if this number is equal to 1, and I'll multiply both sides by C minus A, and I get A minus B equals C minus A. And they want the average of B and C. So why don't we get our A's on one side and our B's and C's on the other.
Okay.
So 2A equals B plus C. Right?
Yes.
So A would be equal to B plus C divided by 2. Now what?
Okay.
What's the arithmetic mean of B plus C?
It is going to be actually divided by B plus.
What we know about
No idea. I'm just staring at this.
What we know about the definition of arithmetic mean is that it's the number of items added together divided by the number of items.
Right.
So the arithmetic mean of B plus C is B plus C divided by 2.
Right, and it's already divided by 2, so B plus C divided by 2, and then divided by 2 again.
Well, no, hold on. In other words, when we solved this equation, we got A was equal to B plus C divided by 2.
Okay,
So
which is already the average.
Yeah, so A is equal to our arithmetic mean. So these two are equal.
Okay.
Okay? All right, let me go to the next page here. 40.
I think I need to learn when to stop trying to, when I get to an answer, that's actually the answer, because I was trying to add an extra step in there.
To recognize it, yeah. Apologize for the quality of this page. It's not.
Well, that's okay, because I can see it fine.
My hand must have been not quite as still. They like questions like this also.
Well, and in this case, let's see, the average of the measure.
I've come across a number of questions like this.
Well, wouldn't they be equal?
Yes. By like this, I meant where they're giving you information that's irrelevant.
Right.
And they like to do that. So it becomes a skill to be able to decipher that. The average angle of a triangle is 60 degrees, no matter what kind of triangle it is, because they have to all add to 180.
Exactly.
And there's always only 3 of them. So. Oh dear. I guess, okay, it becomes clear. When I saw a shaded region, I wasn't sure which region they were talking about until I looked at quantity B, and then it became self-evident.
Okay, and this is going to, let's see.
Let's talk about, unless you know how to proceed here, I was going to say let's talk about the area of shaded regions, because that's another popular question. Let's just take a simple case. This is a typical shaded region problem.
Okay.
And typically, shaded region problems are almost always solved by subtraction. We don't have any formulas to calculate this shaded region. But what we know is that that shaded region in my drawing is the area of the outside circle minus the area of the inside circle.
Okay.
So it's a subtraction problem. We certainly know the area of the outside circle is 25 pi. The area of the inside circle is 9 pi in my drawing again. So the area of the shaded region would be 16 pi. So fundamental to shaded region problems is subtraction.
Okay.
Okay? So what's the area of the striped region?
That is 9 pi.
What is the area of the full circle?
It is 25 pi.
And what is the area of the white circle?
It's 16 pi.
So the area of the shaded region is what?
That is going to be, well, 16 pi minus 16 pi, isn't it?
No, the shaded region would be the area of the outside circle minus the area of this circle.
It wouldn't be minus the area of the striped circle as well?
Well, not really, because if you do that,
you end up with 0.
Well, right. And the area of this region here, the white region, is not the area of that white circle. In other words, when I take the outside circle and subtract out this second middle circle, I'm taking away the striped region also. So that gives me the shaded region.
Right, okay.
Okay, so that shaded region is going to be 25, 9 pi is the shaded region. We already got that, actually. We really don't need the rest of these. Since their question is the area of the shaded region and the area of the striped region, what's the area? I meant to say shaded and area of the striped region is what?
9 pi.
So how do they compare?
the quantity A is larger.
They're the same. In other words, the area of the shaded region was 9 pi, and the area of the striped region is also 9 pi.
9 pi.
Yeah.
Sorry, I had it backwards.
That's okay.
The way I wrote it down, I had it backwards.
Didn't really need to list all of those. I don't know why I was. Usually, probably one of the weaknesses I have is that when I get a problem like this, I like to list everything that I know. And then when I'm looking,
good, actually.
well, I like it, but in some cases it's extra work because you don't really need it. In other words, once I had the area of the shaded region, which was relatively easy to get, then the area of the striped region is just a straightforward. There's no subtraction required there. So there was really only 2 steps here. The big step really, I guess, is in knowing that this shaded region is the outside circle minus the second circle, ignoring the striped circle. In other words, we don't really want to subtract this white region. We want to subtract that whole circle.
Exactly. Okay.
Okay? This is blurry, but I can probably help with some of the numbers here. In fact, let me draw this. Now, notice this is not a grid. This is just a bunch of lines. This angle is 20. This angle is 60. This angle is A, this angle is C, and this angle is B. In the figure below, what is the value of A plus B plus C squared? No, that's not a square, is it? Hold on, let me look in my book where I can actually read it a little bit better. No, that's a question mark.
Okay.
Okay, so what do we know? Can we figure out any of these angles?
Yes, because, let me see, hold on one second. Yes, 20 in A would equal 180 degrees. Is that correct? So wouldn't A be...
Well, now, hold on. 100? No, not really.
No?
Here, let me put this line in here a little bit better so that it crosses that intersection. Let's look at angle B first.
Okay.
Angle B we know.
Okay.
Whenever you have 2 lines cross, this angle is always equal to that angle, and this angle is always equal to this angle.
Okay.
The vertical angle theorem.
Okay.
Geometry. So immediately we know that angle B is 20.
Okay.
Okay. Now we can figure out what angle A is because we know that 60 plus A plus B has to be 180. In other words, whenever you have a straight line, these 2 angles add to 180, but even if I put a third thing in there, then x plus y plus z adds to 180. So if your baseline is a straight line, all of the angles that make up that add to 180.
Okay, so A is going to be 100.
Correct. And now based on the vertical angle theorem, C is what?
And so C is going to also be 100.
Which makes A plus B plus C
220.
Correct. Okay, let me write this. 4 to the 10th times 64 squared equals 16 squared times 4 to the nth. And this is a exponential base problem. Again, this problem would be a little difficult to do in your calculator.
Yeah, what?
The numbers are so huge, it's liable to extend the limit of your calculator. So they don't want you to do it in a calculator anyway. Let's talk about exponential base problems. If I say 8, no, I don't want 8. Let me use different numbers. Let me say that 3 to the x is equal to 9 to the 2x minus 1. This is the type problem we're dealing with. And the reason it is because both of these bases, 3 and 9, have a common exponential base, which is 3. And what that means is I can rewrite the 9 as 3 squared in parentheses. That's the same as 9. Still have to take it to that exponent. But now I can solve it because I have now 3 to the x equals, well, if I multiply that exponent by that, I've got 3 to the 4x minus 2. Now, since I have the same exponential base, this exponent has to equal this exponent by definition.
Okay.
Okay? So that's the way we solve these exponential common base problems. And they can get a little bit more tricky, leaving the numbers that we have here. If I said 9 to the x was equal to 27 to the 2x minus 1, we would solve this in a very similar manner. What is the common, not factor, but the common exponential base of 9 and 27?
3.
So I would write 3 squared for the 9, and I would write 3 cubed for the 27. Multiply these two out, multiply those two out, and equate the exponents when I'm done. And solve that equation for x. Okay?
Okay.
So that's the technique, and we're going to use it on this because what's the common exponential base of all the bases that we're looking at?
4.
Okay, so this is going to be 4 to the 10th times, what is 64?
16. Well, yeah, 16.
It's 4 cubed.
Cubed. Oh.
In other words, we have to relate 64 in terms of 4.
Okay.
Okay, not 16. In other words, what we're going to do is we're going to convert all of these to 4s.
Okay.
Okay, so all I did was rewrite the number 64 as 4 cubed. And then 16 I'm going to write as 4 squared. And always put parentheses around them because we still have to take that to another exponent. Okay, so now let's reduce. This becomes 4 to the 6th equals 4 to the 4th. You see where we're going with this? Okay, can you take it from here?
I think I can. So the exponents would be, let's see, 16 equals 4 plus n.
You got it.
And then subtract the 4 from each side, so n equals 12.
Correct.
Wow, I would never have been able to figure that one out.
Well, it all has to do with exponential base. And when you see a bunch of different numbers, especially with exponents, and if it's a question about exponents, it almost always you're going to want to solve it with that technique. As long as you recognize that there was an exponential base that's common to each of these 4 numbers.
Okay.
Okay. on. Move this out of the way a little bit. Now, this to me is a problem that lends itself to back solving. We haven't really talked too much about back solving, but we ran into a few problems in our last session that had to do with picking numbers and then back solving. But straight back solving is very useful when you can take their question and pick an answer and work back through the math quite easily to see if that is the correct answer. In other words, we really don't need to come up with an algebraic equation for this. Now, what is the first choice we should make? Well, it's almost always B, and I'll explain why. Let's try B.
Okay.
Okay. I mean, it's almost always B unless the question is what's the minimum or what's the maximum, and then of course you start with the lowest or the highest. But when it's a question like this and we don't have anything else to base it on, start with the second lowest. And I'll explain why after we go through this. So if the present cost, so you start off assuming the present cost $80.
Okay.
And now we'll see if that makes everything else true. And if it does, that's what the present cost. And then we got our answer. If it doesn't, we'll have information to know, well, we need a bigger number or a smaller number. So if the present cost $20, how much did each child supposed to put up?
Each child, if all 20 would have, it would have been $4.
Right, $4 each. Okay. So 4 of the children decided not to contribute, so there were 16. So 16 kids had to pay $5.50 each. Right?
Yes.
Does that make sense? Is 16 times $5.50 equal to $80?
No, it's too much.
It's too much. Okay? So since it's too much, we probably need a lower number. I mean, we're not 100% sure, but it sure looks that way to me. And in a lot of these problems, you're always going to know whether you need to go lower or higher. Some of them, not all of them, but I would say half of the problems that are perfect back-solving problems, problems like Joel is 30 years old today, 6 years from now, he'll be twice your age, how old are you? Questions like that, when you use a back-solving approach, you always know whether you need to go younger or older. Just it's evident. Well, this one, I'm pretty sure that it's evident that we need a lower number, which means we have the answer, 50.
Right.
But let's just check to make sure. You wouldn't always need to do this if you were completely sure. So if the present cost $50, how much would each of the 20 kids, what would be their share?
$2.50.
Okay, so each would have to pay $2.50. And now if we check what the kids would have to pay with 4 of them not paying, we would have 16 times
4.
Which is 64, which is not
so I
50.
did something wrong with my math.
Right,
Sorry.
which is not 50.
No.
That doesn't work either. So this fooled us into thinking we had to go smaller. We actually had to go bigger. Okay, now here's where the trick comes in. What is the next number we're going to test?
D?
Yes. D will tell us the answer with just one more test. No matter what we get, D is going to tell us the answer because either it'll be correct or we'll know we have to go smaller or we'll know we have to go bigger. So the beauty of back solving is that you don't, almost never do you have to test all 5 solutions. Usually you test at most 2 solutions and you have your answer. So if the present cost $120, each child should have to pay 6, and then 16 kids would have to pay $750, and 6
and that works.
times 750 is equal to 120, is it?
Yes, it works.
Okay, so that's our answer. And by this point, if 120 wasn't correct, we would definitely know whether we needed more or less.
Now, what I did on the first one with the $80, and I ended up coming up with $88, so I thought I needed to go smaller.
Yes, that's what I thought also.
Okay, I was going to say, should I just have...
No.
Yeah, I'm really glad you said to check it, because I think I probably would have just picked A.
Well, that becomes a little tricky. Sometimes you're 100% sure which direction you have to go, sometimes you're not.
Okay.
In this case, I was not 100% sure. If I was taking this test, I would have thought lower also, but I would have checked it.
Okay.
Not always. If it's an age problem, there's never any question about which direction you have to go. And there are some age problems in these tests, so we'll get to do one of those.
Okay.
But this one was a little tricky because it did suggest the wrong direction. But once we figured that out, in other words, when we picked 80 and we came up with a number that was less than 80, now we know that means you have to go bigger.
Got it. Okay.
In other words, if we'd have picked 150, we're going to come up with a number that is greater than 150. Let me show you. Okay, if we pick 150, divide that by 20, each kid has to put up 750. So now we have 16 times 9, which is 144. Makes you think you need a bigger number.
Right.
In reality, you need a smaller number.
Okay.
So sometimes it goes opposite when you come up with your answer from the way you think. But once you're shown that, now you know. In other words, if I hadn't have done D and I'd have gone to E immediately, well, of course, I know that it has to be smaller because there's no other answers there. But,
right.
but I would have known that anyway, merely by the fact that I knew that when we came up with a number that was less than that, we actually had to go bigger. So the other way would have to be the opposite.
Okay.
And I would know that. I tend to lose track of time sometimes when I'm tutoring, so if I go beyond our time, you let me know.
Okay.
Okay. 200 seniors, exactly 40 are in the band, 60 are in the orchestra, and 10 are in both. How many seniors are in neither the band nor the orchestra? You familiar with Venn diagrams?
Can this one actually be answered? Let's see.
Maybe.
Isn't there a both equation where you can add them and?
Well, this is actually a classic Venn diagram problem. And
is it okay?
Yeah, and it probably, we want to go over Venn diagrams because they're full of them, where you kind of have to use the Venn diagram approach or a table approach sometimes. But
Okay.
this is a real clear Venn diagram, and the reason it is because there's 4 choices. There's the total students. We've got students in the band. We've got students in the orchestra. These are students in both, and these are students in neither. Everything has to total 200.
Okay.
Okay? So if 10 are in both and 40 are in the band, that means that has to be 30. And when I say, when I put the number in this part of the Venn diagram, I'm only using this amount.
Okay.
In other words, I'm separating the both from the ones that are in band only. So 30 would be in band only. And 60 are in the orchestra, but 10 are in both, so there must be 10 orchestra people. So this has to be 50.
Okay.
Now how much is neither?
80.
Well, this totals 90 because we've got 30 plus 10 plus 50.
Oh.
Remember, these numbers I'm putting in here are exclusive to their region, not,
Okay.
in other words, it's not 30 members in the whole circle. It's 30 that are band only, 50 that are orchestra only, and 10 that are both, which
Okay.
110 for neither. Now, sometimes Venn diagrams are used when you only have 3 possibilities. And so you don't have 2 circles and a rectangle, you have 3 circles. Something like that. But same technique. We'll come across more Venn diagram problems before we're done. Once you figure out the methodology, they become fairly straightforward. But it's really helpful to use a Venn diagram. There may be an algebraic way of solving that. I don't know. I've gotten
but that was a lot simpler.
Yeah, I've gotten so used to using Venn diagrams, and and there must be some reason that they teach them to us. It's probably the easiest method to solve it, even if there is a more complicated algebraic method. Okay, here, let's let me see. I don't know. Yeah, that might be readable. Let me open the next page here. Not readable there, but that's weird. Let's see. This is a little more readable, yeah. You put this one there and this one over here. And no, it's not going to be readable enough. Well, for now, let's bypass these questions based on graphs. I don't want to do that permanently because there's too many questions like that on the GRE. So what I'll do is scan these with my scanner, and we'll go back and redo some of these at a later time when we can actually read them on my computer. Because there's 3 questions, 14, 15, and 16, that require us to read these 2 graphs here.
Okay.
They're just not that legible on my computer screen.
Yeah, I can't really see the numbers either.
No, I could tell you what they are, but it would just be too difficult to go through all of that. So let's just skip past those 3 questions and go to the next page. And it'll be easy to remember that we haven't done any of these, so it'll be easy to go back and pick them up once I get them into the computer. Wow, this was fine. I'm Must just not have been able to hold the camera steady enough on those. Okay, so let's look at 17. You read 17?
Yes. So this one I assume I would solve algebraically.
Yeah, I think that's probably the easiest thing to do.
So x plus 3 plus 2x minus 3 plus 3x minus 5 equals 25.
So that simplifies to that. So 6x equals 30, x equals 5. And if x equals 5, you got to be a little careful here. They love doing this also, which is to ask you a question, we solve for x and immediately answer a. And that would be incorrect.
No, we need to put the 5 into the equation.
And figure out which of these is the smallest number when we put 5 in.
Okay. So
And it's the middle one.
Okay.
7 is the length of the shortest side, not 8, and not 5.
Okay, so yeah, answer C.
Okay. All right, let's do one more here.
Okay. Okay, yeah, this is one of them I definitely could use help on. I have a difficult time with ratios.
Well, everybody does, and this is actually fairly tough to solve algebraically. Very confusing. So whenever you have a problem like that, if you have a choice and can pick numbers, let's do that, and then the problem will become real easy.
Okay.
So
once again, I think I'd start with 100.
Okay, so we got 100 girls and 50 boys. So from 1990 to 2000,
The number of girls increased by 25%, so it'd be 125.
okay,
And then the boys, it would end up being, well, you know what? Let's see what the boys.
okay, this is an excellent example of sometimes you pick numbers that don't lend themselves to the figures they're giving you.
Right, and this one doesn't.
Exactly. So how do we solve that? Let's go back and pick numbers that are going to be, that we can multiply by 25%, and 25% would be a whole number.
Okay.
So how about we do 200 girls and 100 boys?
Okay.
And now the girls go up to 250, and the boys go down to 75.
Okay.
So a lot of times when you pick numbers, the secret is to pick the right numbers, and that usually is governed by whatever we have to do to those numbers.
Okay.
Okay? So what's the ratio in 2000 of the number of girls to the number of boys? That's pretty easy.
Yeah, it's 250 over 75, and then reduce it. And of course, I can't reduce it in my head here.
Well, I'm not seeing an answer that is that answer.
I'm not either.
Is this a trick question? Okay, their answer. A nice way to answer it is to pick numbers. Assume that there are 200 boys and 100 girls. So that's where we went wrong. Twice as many boys as girls. So the boys are up here, the girls are down there. The boys dropped by 25% to 150. The girls went up by 25% to 125. So our ratio of boys to girls is 150 to 125.
Okay.
And that reduces to 6/5. In other words, we can divide 5 into both, or we can divide 25 into both, top and bottom, to get that.
Got it. Okay.
Okay, that last step is relatively, you don't need help there. You could always use a calculator and figure out which fraction is equal to that number.
Right.
The key here is we both made a mistake. We got the first part of it backwards. But they were nice enough not to put that answer as one of the answers. Had the answer,
which is good.
Yeah, whatever that reduced to, 25 goes into the top, 10 goes into the bottom 3. So there should have been our answer, but we didn't see anything like that on there. So that is a clue that we made a mistake in whatever we were doing.
Okay.
And a very helpful one. And as long as they don't put the trap answer on there, we're fine. We got time to save it. And we were able to by going back and rereading the problem and realizing we got the first part of it wrong, or first part of it backwards. Okay?
Thank you.
Yeah, you're welcome. I think this is a good test here, and I've got
Yes, it is.
Yeah, I've got 4 or 5 more from this same book, not diagnostic tests. We're about done with this because I think there were just 20 questions. Yeah, but a lot more practice tests also. Okay?
Okay.
All right, Angela. Let's see. Do we have another session set up yet, or you're
not yet?
You're comfortable with doing that on your own?
Yes, I am.
Okay, great. I will talk to you next time.
Okay, thank you.
You're welcome. Bye-bye.
Bye-bye.